I can use that one. Which do you prefer? As you wish. Can you try this one? Does it work? No. No? Does it work? Good. Okay. Thanks a lot. So I'm Olivier Melançon from Université Montréal in Canada. I'm going to present today an executable semantics for faster development of Python optimizing compiler. And the co-authors for this paper are Marc Feeley from Université Montréal as well, and Manuel Serrano from Université Côte d'Azur in France. Okay. I want to start by giving a few motivation about our work. So we are working on optimization of dynamic language, and in the last few years, we've been working in particular on Python. And through writing quite a few implementation of Python, we came to realize across the years that every time we implement a new Python compiler interpreter, we just find the semantics to be really complex and really error-prone. And this is an optimization problem because all the time we spend on getting the semantics right, we just don't spend on doing optimization, which is our goal. So we came up with that goal of writing an executable semantic, which will automate that process of implementing the first few steps of the semantics of Python, but we also want it to be reusable, so we can reuse it on every new implementation we write, and hopefully we want it to be somewhat performant. So this semantic is what I'm going to present today, and the talk will be in 4 parts. First of all, I'll give an overview of Python semantic. If anyone is not familiar with Python in here, who's familiar with Python? And Python implementation? Okay, yeah, so first part will be necessary. Then I'll show the executable semantic and discuss optimization with a partial evaluation technique, which applies specifically to this semantics. And then I will finish with example of integration of this semantic in one of our compilers. 1 second, there we go. Okay, so first, why Python? You've probably heard that a lot. Why Python? Because it's popular. Right now on the TIOB index for this month, it's still first, once again. And it has somewhat uncompetitive performance. CPython is known to be slow, and it is known that it has a lot of superfluous instructions, such as method call, boxing and unboxing of primitive values, and a lot of type checks. And we have good implementations. For example, PyPy is one of the state-of-the-art implementation at the moment, but we still need better implementations. So why is it hard to implement Python semantic? Well, I'll give an overview of the semantic, and I hope you'll understand. First, Python is an object-oriented language, and in Python, everything is an object. And by everything is an object, we mean that everything has an ID, which is a unique identifier, a type, and a value. And I want to go deeper into the type. What a type is another object which has attributes, which are methods or functions, if you'd like. And depending on which function are on the type of an object, you will know which operations are allowed. So for example, for an object to be addable, so if you want to be able to do addition, it must have the double underscore add method. And you'll see that convention, double underscore something. This is how those methods that implement operations are called in Python. So let's give an example of what that looks like. If you have the operation 1 plus x, and say x is 2 here, how will Python compute the value of this expression? Well, first of all, Python will take the left-hand side operand and check its type, which is the int type, integer type in Python here. Then it will try to look for the add method of this type, and if it exists, which it does for the int type, it will call it with the left-hand side and right-hand side operands, and this will return 3. No surprise here. And this is actually an easy example because everything went smoothly. So the add method exists, and then the add method, of course, expects to receive an integer as second argument. So let's see what happens if we have a more complex example. We have the same expression, but this time x is actually a programmer-defined type with the class keyword. So the same happened at first. We get the type of the left-hand side, then we find the add method, then we call the add method, but then we have a problem because X is a programmer-defined type. So add doesn't know what to do with this method, and it actually returns not implemented. Not implemented is an object. Everything is an object in Python, but it's a special singleton which tells the semantic of addition, well, this method here, it doesn't know what to do with X. So what Python does, it falls back on the right-hand side operand, and here let's say X as type T, then it will go get the double underscore R add. The R here stands for reflected, so we fall back on the reflected addition method, and we call this method here. And hopefully it returns some result, and if it cannot, for example, if it returns not implemented, then we raise a type error, and we cannot do addition. And basically, all operation, arithmetic operation, unary operators, comparisons are done the same way. But the name of the method, for example, will change. So for addition, we have double underscore add, but for subtraction, we will have double underscore sub. And there is one last complexity which I need to mention. Well, Python supports inheritance and actually multiple inheritance. So when you do that method lookup, looking up for the add method on in, for example, you don't just look on the type, you actually have to look on the type and all of its parents. So there is this linear lookup of methods. And since types are actually objects and are mutable, you cannot pre-compute, in general, this method lookup to execute operations. And semantically, if you have a direct implementation of this semantic we just described, well, there is a significant overhead because we've seen just for addition of 1 and 2, we have one method lookup, we have one method call, and we did not talk about what happened inside the method call where the type checks and boxing and unboxing lie. So it's quite a significant overhead for adding 2 small integers. And we come back to that executable semantics that we wanted to write to be able to implement all that behavior that we've seen and just be able to reuse it, to have it in some format which we can reuse when we start an implementation. So what we did is we went on the Python official documentation here, and everything I've just described, that's what is highlighted in yellow. So this is from the Python official documentation, and our goal is to convert this into some form of reusable format that we can reuse across compilers. So the first attempt we had was to write that in pseudocode, at least to guide us. And here you have the implementation of this addition, which go get the add method and calls it. And there is the pseudocode implementation of the fallback on the reflected addition method. And we see that in the end, at the last line, if nothing worked, we raise a type error. So that's the pseudocode implementation. But we cannot reuse that, so we try to write it in plain Python so a compiler can just read it and integrate it. Our first attempt looked like this. So we define a Python function which is called add, and it has 2 branches. So you have on the left you have the add pseudocode which correspond to the normal nested function, and the radd correspond to the reflected. And the trick here is to use the built-in function get attr in Python, which looks for an attribute or a method on an object, which here is the type of X, for example, and can take a default value which will be returned if it is not found. But there's a problem with doing that. Actually, there are 2 problems. First is the get attribute built-in function will have its own semantic. Getting an attribute in Python looks for the double underscore get attribute method and calls it. And that's actually not what's going on when you have an addition. You want to do a simpler kind of lookup, which is looking at the type and its parent for the method add. And we also cannot use none here because none could end up being an attribute. So this first attempt did not work. And what we found out to work was to add primitive to our implementation. So we still write it in Python, but we ask the compiler which wants to read this semantic to recognize some primitives. So you have 2 primitives on the left, which are class get attr, which does that lookup on the type and its parent. And this function here will return another primitive, which is called absent. It's just an object we can recognize by identity if it is not found. And this here actually works. If your compiler or interpreter can recognize those two primitives, you can make it digest this semantic and use it at runtime. The only missing part is the actual method. Some of the logic happened in the method, and we did not define those yet. But we found that we can actually use the same strategy, that is, say, well, we'll write the int type, for example, in plain Python. We'll just add a few primitives to manipulate native values in the host language. And here we have two primitives which we use, which are called int to host, which takes a Python integer and unboxes it to get the value in the host language, and int from host, which does the reverse. It takes a host value and it boxes it into a Python integer. And so the add method, what it does, well, it takes x, it takes y, checks that they are both integers, then we'll unbox them, add them in the host language. For example, we'll add machine integers and then box them back to Python. And this here is the semantics of Python addition of integers. So if we just recap, what we've done is we added 4 primitive class get attribute, absent, into host, and in from host. And with that, we were able to get a semantic which can be, if an implementation has those primitive, which can be digested by your interpreter and used at runtime. And you can actually, and we've done the same for other operations, such as other arithmetic, comparison operator. We've done it for truthiness, subscription, attribute access, iteration. You can define all of those operations with this strategy, because all they do is just get some method, call it, and maybe return a result. The question now is, what about performance? And the answer is, well, at that point, there's no change, because we've shown where the type checks are, we've shown where the magic method are being recovered, but we did not remove them. And this is where partial evaluation of the semantic comes in. We at some point realized a key fact about Python, which is really handy. It's that, and this is the case for CPython, PyPy, so we take it to be part of the semantics. When you have a built-in type, its methods cannot be mutated. So I said that types are mutable, but that's only for programmer-defined type. And so there is this idea that if you have a built-in type, well, probably that some of those boxing and type check can be removed. And we can actually remove them. I'll give an example with our definition of the semantic of truthiness. So in Python, everything is either truthy or falsy. And in particular, when you have a container, such as a string or a list, it will be truthy if it is not empty, meaning it has a length which is non-zero, and it will be falsy if it has a length of 0. So suppose you give a string to the truth semantic here. What will happen is, at first, Python will try to get its _bool method, which will give its truthiness. But on strings, since it's a container, the bool method doesn't exist. So what Python does is it falls back on getting its length and check if it's 0. And this is actually done by calling a semantic in its own right, which is the length semantic. So the length semantic tries to get the length method, which exists on string, tries to call it, and calling it does this here. So we have an implementation of the length method of string. And what it does is just it checks the type of its argument, then gets the length with a primitive which we call string length to host. And then this length, it boxes it to a Python integer, returns it, and compare it to 0. But since we know that for built-in types, methods are immutable, everything which is in red here, we actually don't need to do if we know that the object is a string. So we don't need to look for the bool method. We know that we're going to call the length semantics. And in the end, we know that it's just this line we're going to execute. And we're just going, on the left here, to compare the result of that to 0. So computing the truthiness of a string should just use this quick path here and compute this result. And actually, we can do slightly better. Notice here, the comparison, the not equal to 0, is comparing to Python integers. You can actually go a bit deeper, and there is a boxing which is not necessary here. You can do the comparison between a host integer and the host length, and then box that as a Python Boolean. And this here, on the bottom, is what we call a behavior. A behavior is a special case of the semantic without all those magic methods. It's a fast path when you know the type of your operand for some operation. And we can write them in Python, so the compiler can compile them and reuse them with a few primitives. But there are dozens of methods, dozens of types, so we cannot do that by hand, and the goal would be to automate that whole process we've been through. And this is where our partial evaluation comes in. We wrote a tool which is called semPy for semantics of Python. I was also doing karate at the time, so I called it semPy. That's the name. What it does is it takes an operator, which could be, by example, the operation for addition. It takes a type context, for example, that x and y are int and float, and it outputs the corresponding behavior. And the neat thing is that semPy can do that only using 3 simple transformations, and it works with those 3 transformations for all operators. It does aggressive inlining of all method calls and semantics. For example, that call of length inside truth, we've seen earlier, it inlines it. It does branch resolution. Since it has type context, it can remove type checks, check that a result is not implemented, and check that a method is not absent. And finally, it can remove those redundant boxing and unboxing at the end. And what it will look like, you give it a semantic on the left, and semPy will know that if x, for example, and y are both integers for addition, well, this class get attribute will always return int.add. It will always return the add method of int. And then we know that, well, int.add is not the absent primitive, so we can just prune out this branch. And then we know that we're calling int.add, so we just inline it. And on the right here, you see what we've seen earlier, that the add method with the type check on x and y, checking they are int, and then unboxing them, then adding them. But in the context where we know that x and y are integers, we can also remove those types, type checks on the left, and we end up with that result is equal to the boxing, unboxing, addition, and then boxing back. And we know that this is not implemented, so we can remove the final branch right here on the left. We can remove the branch result is not implemented, and we get to this behavior. And we've just used those 3 transformations, and the neat thing is it works for all arithmetic, comparison operators, and so on, with only those 3 transformations for all numeric types. And the goal is then to use those behavior and integrate it into a compiler to see the performance we get. So first of all, I want to point out that those behaviors we generated are actually independent from the compiler. As long as your compiler is able to parse Python syntax, which it should be able to do, and it knows those few primitives, then you can just make it read the primitive, integrate it in the compiler. And what we've done is we have our own prototype of Python, which is called Zipi. And what Zipi does is it just reads all those behavior, compiles them, and when it executes an operation, instead of doing that whole method lookup and then calling the method, it just looks at the left-hand side type, look at the right-hand side type, and dispatch to the correct behavior, which was pre-computed. In terms of performance, that's what it looked like. So here, what you have is a comparison between Zipi, PyPy, and CPython. In green, you have Zipi. In yellow, you have PyPy, and CPython is the baseline. So here, we're comparing how much faster we are than CPython. So higher is actually better. And on the left, what you can see is that we are, for at least benchmark, which are very arithmetic intensive, we are not only way faster than CPython, on some benchmark we are faster than PyPy. On the right, still, you can see that Zipi it's a prototype, it's a work in progress. There are some features which are not implemented at all, so it's not surprising that we see some not arithmetic intensive benchmark to be fairly slow. So I want to conclude quickly now that where we came from is that we found out that Python semantic is just really hard to get right when you write compilers, and it also has those redundant operations such as method calls and boxing and unboxing. So we wrote that semantics so that it is not only reusable across compilers, but it also highlights these operations which are redundant. And through partial evaluation, we can generate those behaviors, those fast paths for an operation for some given type. And as I've shown in the last slide, it gives us a fairly good performance on arithmetic operations. In the future, what we want to do, well, we only implemented those that semantic and those behavior for arithmetic operation, and comparison operation, and truthiness as well, but we want to extend it to iteration, subscription, calls, and we should be able to do it because all those do is find the correct method and call it. We also want to apply type analysis to better dispatch those behavior, because right now in Zipi there is no type analysis at all. It's just operations which are locally optimized. And one of the methods we want to use is basic block versioning. We will be looking into that in the future. And finally, all those behavior right now are generated ahead of time when you build a compiler, and we are interested in looking at what it would look like to generate them just in time. So that concludes the talk. Thank you very much, and I'll gladly take questions.
Thank you, Olivier. Do we have a question?
Yes, thank you. Very important work giving the energy footprint that Python has. I wonder, are you dealing with dynamic binding? Dispatch. And independent of your answer, I'd like to point you to Smalltalk. Smalltalk has dynamic dispatch on true and false. And this is how it implements if then else. And actually, it only has so in the book. No Smalltalk system ever does that. So they actually do what you do. They translate this to ordinary branches, sort of optimize the implementation there silently. Even though you can look up the methods for if then else, you cannot really change them because the compiler does some magic there. So, and this relates to dynamic dispatch. So have you looked at it?
Yeah, we've had a look at Smalltalk, and we also know that even CPython does that in some occasions because just looking for the method for adding two integers, it's just way too slow. And yeah, to answer the question, yes, we had a look at Smalltalk. And just to be specific about what we do, to get those results, we have those behaviors, and we know that some of them are actually called more often. For example, addition of two integers. So what we'll do is each type has an index, a unique index which represents it. And if we see that the index of the left and right operands are either two integers or two float, what we will do is we will inline so we will do speculative inlining of the behaviors for addition of integers and float. And otherwise, we have that big table, and you can take both indexes of those types and find where the behavior is. I don't know if that was the question, but thank you.
Okay. Thank you for your talk. It was really highlighting. I was just wondering, Python is a strange language. One that you can use something like subclassing, standard classes, and then you can use this to bring in the class. How can your system can work in these cases when the system classes are just another class?
Okay. So we're really using this trick that you cannot do that with built-in types. So we can only apply behaviors with built-in types at the moment because we know those methods will not change. And in the future, one of the interesting things to do would be to implement behaviors just in time with the known method which some programmer-defined type has. And what you can do is, if ever you detect that this method changed, you just de-optimize the behavior. But we could still generate, because most of the time methods do not change, you just have to de-optimize when it happens. So in a just-in-time context, there should be a way to do that. You just have to be ready for some de-optimization.
Okay, maybe a last question?
Yeah, thank you very much for the talk. I was just wondering if in some way you are clarifying the Python semantics at the implementation level. And I was just wondering if you, what you think about trying to abstract a little bit this at the specification level, such as we can have more reasoning, composability, and so on in the semantics. And then having a generator for having all the optimization that you demonstrated. Is that something that you think about, or what's your opinion on this?
I think what you're mentioning is one of the ideas we have with just-in-time generation of those behaviors, because right now they are somewhat really local. It's only a behavior for addition of two types, and you have some information that comes in, and you should know that when you add two integers, you get an integer out. And right now we don't even do that. So with just-in-time generation of behavior, what you should be able to do is you have x plus y plus z plus, you have an expression, you check the types beforehand, you generate the whole behavior for this complex operation, and then you can run that. So that's where we're heading with just-in-time behavior generation.
Okay, and you don't think that's something that we could abstract a little bit in a specification language, and having a meta language for specifying exactly what you will demonstrating instead of being at the implementation level?
I'll have to think about that. At the moment, I don't know. The direction we're really taking is trying to get that type information which is lost when we leave behaviors, but I don't know yet. I'll let you know next time.
Okay, thank you again.
Thank you.